Good morning. I hope that everyone is in the right place here for this session on liquefied gases and compressed gases. We're going to be going over quite a few things today. We're going to start off with some basics on risk management. And so bear with me for the first half hour or so. It's going to be some basic concepts in risk management. And then we're going to get into discussions of physical properties. And I'm trying not to repeat a lot of things from one session to the other in terms of some basic concepts. So I just want to warn you that if you only choose one or two, you're going to miss some of the things because I'm not going to go over some of the basic concepts about each gas in that session. I'm going to give examples and they apply generally, and I'll try to make that clear. What's the purpose today? And by the way, I thought I was going to have the ability to move around. I have to stay right here because we don't have a remote slide advance. So I was going to try to go and ask people in the back of the room a lot of the questions. That's another reason to move to the front. But what are we going to try to do? This is a session that's intended to look at some of the basics in terms of risk management and talk about the difference between preventive, protective controls and mitigative controls. And I'm going to give a lot of examples of where both types of controls have failed. We're going to talk about specific hazards and risk management practices throughout the supply chain. And when I put this course together, I put it together to be generally applicable across the U.S. And so I'm going to give a lot of examples that are not California specific, but they're things that can go wrong. And there are other places in the U.S. that are outside the U.S. in terms of major disasters that have occurred in terms of releases of liquefied gases. We're going to talk about a lot of different kinds of liquefied gases, and we'll get into how people categorize compressed and liquefied gases. In terms of looking at some of these serious incidents, I'm going to talk about the immediate causes in terms of what initiated the events, and then in many cases also talk about underlying root causes. And I won't be able to do that for all of them because in many cases there aren't very thorough accident investigations publicly available that go into that depth. And where there are, I'll talk about them. Now, who's the intended audience here? Quite a wide group of people in terms of those who design and install liquefied gas storage facilities, those who are involved in the operation and maintenance of those facilities, those who have to regulate the installation or operation of those facilities, or first responders. So let's start at the back. How many first responders are here in the audience? Couple. How many folks are with the state or a CUPA, county CUPA? And how many of you are from the private sector, a company that uses or transports liquefied gases? And how about anyone who designs systems and supplies liquefied gases? It's probably going to be too elementary for those folks. Okay, I see we've got a pretty broad cross-section, so what I'd hope for is here. Now, during the day, we're going to talk about in these different sessions different gases and some different emphasis. In the first session, as I mentioned, we're going to talk about some basics on risk management. I'm going to talk about specific properties as to how one can determine whether or not a gas can ever be liquefied. And so by the end of this session, when I tell you a gas and I tell you a certain property, which is called the critical temperature, you're going to be able to tell me at room temperature if in a cylinder that gas looks like this or it's like this. It's a gas or a liquefied gas. And there are a couple other things you're going to need to know in terms of vapor pressure as well, but that's one of the goals. That's one of the take-home lessons that hopefully everyone will be able to take with them. We're also going to talk about certain asphyxiant gases and what the hazards are, and the differences between these two particular asphyxiant gases in terms of physiological effects. The second session, we're going to talk about flammable gases, and I said in the abstract I was going to put hydrogen in there, and I did not. So if any of you are here to hear hydrogen in the second session, I apologize, but I just don't have enough time. Next year we're going to do hydrogen. In the third session, I'm going to talk about chlorine and oxygen, with most of the emphasis on chlorine. And again, like in the case of propane and chlorine, I'm going to talk about a lot of case studies where things have gone wrong, people have died, major releases, with some videos for propane in particular. And then at the end of the day, ammonia and SO2 were on the agenda. I had 3.5 or 4 hours of material on ammonia that I boiled down to 1 hour and 45, so we're not going to talk much about SO2. Again, that's going to be more next year, I think, so just to give you an overview. Now, in terms of this first session, we're going to talk about some basic concepts now and then get into properties. So, first of all, hazard versus risk. And the reason I want to bring this point up is that what we're striving to do is contain these hazards. And if you look at the definition for process safety, which is a lot of what I'm going to be talking about, versus worker safety, can anyone tell me how they, in one or two sentences, would differentiate between process safety and worker safety? Anyone want to volunteer a definition? I'll give you one. Keep it in the pipe. Process safety is all about preventing loss of containment. And preventing loss of containment can prevent worker injuries, but can also prevent property damage, it can prevent environmental harm, it can prevent off-site consequences in terms of injuries to the public, to neighboring properties, etc. And the subject of risk is we're going to look at if we've got a hazard contained, whether it's chlorine, propane, ethane, ethylene, electronics industry gas like silane. When it's in the cylinder, when it's in the tank, when it's in the pipeline, it's contained. But the hazard, the inherent characteristics that make that material hazardous are still there. It's contained. And the job of individuals like myself, and Kristen, by the way, told me to introduce myself, which I didn't do, so I'll do it as we go through. But one of my jobs as a chemical engineer is to figure out from an engineering standpoint and a management system standpoint how to keep the liquefied gas, or whatever the material is, contained and not released unintentionally. Now, in terms of risk, what we typically do in looking at situations is we can't eliminate all of the risk associated with a hazard, but we want to minimize it and get it to a level that is at least tolerable. So I'm going to be talking about tolerable risks. And one of the things that we have to all be constantly on guard for is to prevent getting complacent about these hazards we deal with. And some of these examples I'm going to show you where hundreds of people were killed. In the area of propane, how many of you think there were or have heard of incidents where hundreds of people have been killed from propane releases? Does anyone know of an example? Yes. I don't know about Texas, Mexico City, 600 or 700 people in the 1980s. But I've got a lot of examples where dozens of people were killed, levees and so forth. So the industry as a whole has an excellent safety record in dealing with liquefied gases, but there are areas that we can still improve, and we're going to be talking about. Yes, sir.
Recently, the natural gas explosion in San Bruno
Yes. Yeah. 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 So I'm going to repeat that because there's not a microphone for the gentleman in the audience just mentioned the example of San Bruno where we had a natural gas pipeline release. And by the way, I've got in here, I was going to talk a little bit about liquefied natural gas, and we'll get into the subject. That happened to be compressed gas. But next year, we're probably going to talk about, when I give the course, if I do, it'll probably also include liquefied natural gas, which is going to be much more widely used around the world. And certainly now in the U.S., we're going to see more export terminals for liquefied natural gas. Now, in terms of risk, this is a very simple risk matrix. 3 by 3, low, medium, or high, and they can be 5 by 5 matrices, 6 by 6, and then you can get into quantitative risk assessment. And the important thing that I try to emphasize is that the most important aspect is to consider the risk, whether you do it in a qualitative, semi-quantitative manner, but you have to be looking at what are the potential consequences, and then what's the probability that that consequence you're worried about is likely to actually happen. We'll talk about some of these events, and you can see, even though we've gone for decades in many locations without a serious incident, it doesn't mean that it couldn't happen tomorrow. And we'll talk about why it sometimes happens tomorrow, because risk controls that were put in are not maintained. They're not inspected, tested, calibrated, and maintained, and individuals are not trained to understand the importance of those risk controls. Sources of information. There are a lot of them out there, and I'm just going to touch on some of them. And one of the things I'm going to try to do during the day is to point out where you can get more information. Of course, you'll probably know all of the regulations. There are a lot of national consensus standards. There are a lot of industry consensus standards and guidelines. And when we talk about chlorine, I'm going to talk about the Chlorine Institute and the many, many things they offer. When we talk about propane, I'm going to talk about the Propane Industry Association. And we'll be able to look at some of the materials that are provided, the Chemical Safety Board, which provides lessons learned. And so there are a lot of different things out there, the technical publications with various professional societies. There's the Coupa Forum presentation records, which are an excellent source of information on the website. So there are a lot of things out there to help you help your regulated community manage these risks. One of the basic concepts in risk management is the concept of layers of protection. We often don't have just one layer of protection. And one of the examples I'm going to talk about in the session on chlorine is where one company depended on a single layer of protection in terms of administrative procedural controls, and they failed. And that's often the case when you have just one layer of protection. And we're going to be looking at, we often have multiple layers of preventive measures. And what are preventive measures intended to do? On the risk equation, preventive measures are intended to reduce the probability that an event will occur. So when you hear about preventive safeguards and mitigative safeguards, it goes back to risk. Preventive safeguards are intended to reduce the chances that you're going to lose containment. Mitigative safeguards are put in place to minimize the severity of the consequences if a release occurs and to minimize the extent of that release. And I'll talk and give examples of different types of mitigative controls as well as preventive, and also where they failed. Now, this whole concept of layers of protection, and there's a whole process within the chemical engineering area called layer of protection analysis that looks at the risks and how to manage those risks and how many layers of protection we need. This concept was discussed, if you want more information, by James Reason in Managing the Risks of Organizational Accidents. And he talked about the concept of the Swiss cheese model. If all of these layers of protection or barriers were 100% effective, we'd only need one. But they're not. I'd spent a lot of my career working on chemical process development and taking new processes into pilot plants and then into manufacturing and working with manufacturing organizations. And when I wrote procedures, I always anticipated every contingency, right? I always could envision anything that might go wrong. And then when I gave the training, all of the operators, just like you, hung on every word I said. And when they left the room, they remembered everything. Those were golden wisdom, nuggets of gold that they walked out of the room with, right? And the training only lasted 8 hours, and they were attentive every minute, right? We have failures. Sometimes people forget to put on their protective gear. Sometimes people do a maintenance task incorrectly. Or they've got a part left over at the end. And I'm going to talk about that. In an accident in France with a bolt in the automatic shutoff valve, they had a perfect design, they thought, but it didn't work because of a maintenance problem. So this is why you have multiple layers of protection, because things go wrong, and eventually, if all of the holes align, you're going to have a release. Now, when you do accident investigations, accident reports, I have had to do a number of those. And when I have read over the years accident reports, 90+% have as the initiating cause what? Human error. And you can look at accidents taking off from runways and turning on the wrong runway, pilot error, all sorts of issues with human error. But my contention is human error, in terms of operator error, that's an initiating cause. There's another human error that was way back there. It was probably a design error or an error that someone made in setting up the management system with the root causes for those events. Deviations and causes. When we set up these systems to control and prevent loss of containment, we typically will have operating ranges. We'll specify, for example, if we've got chlorine, that we're going to design this process and this storage facility to operate at below 250 pounds gauge pressure. Now, if we have a storage vessel that has a working maximum allowable working pressure of 250, it's going to have a pressure relief valve on it. Now, what could a deviation be? Let's say we suddenly see that tank is now recording and it's supposed to be operating in the range of 75 to 125 pounds gauge pressure. So suddenly the pressure is now up at 225 psi and climbing. And we see that on the control panel. Now, what could a reason for that be? One of the reasons could be temperature, vapor pressure. That chlorine tank looks like this inside. It's got a liquid in it. That liquid has a vapor pressure. As the temperature rises, the vapor pressure rises. Now, what could cause the temperature rise? There may be a fire, and there may be direct flame impingement or radiant heat. So that's why we've got the deviation. The cause of the deviation is the fire. The deviation is the pressure excursion. If left uncontrolled, and this gets into this whole concept of layers of protection. And I also, when they didn't give me, I don't have my little laser pointer. So I'm going to step down. So here's what I talked about. Well, here we've got, let's say we've got our chlorine in this storage tank and system. It's contained. It's all controlled. It doesn't mean the hazards have gone away. They're still there, but they're contained. Now, this concept of multiple layers of protection. Let's say we do get a deviation. We have a fire scenario, direct flame impingement on the vessel. So what could bring this back into control? We might have a mitigating measure. If it's a fire situation, we're going to have some kind of mitigation control in place. And what's that likely to be? It's likely to be a deluge system to put out the fire to stop the excursion. Now, there's also probably going, if it doesn't put the fire out in time, there is going to be a release. There's an additional layer of protection. It's the pressure relief valve. And we might have two on there. We may have redundancy. So there may be two layers of protection, and we're going to eventually get to a safe shutdown condition. Or, if we don't get to a safe shutdown condition, in addition to the fire suppression system, we may have a scrubber on the vent line so that we've got a caustic scrubber to produce bleach so that we have low to moderate severity of an incident. So that's the concept of multiple layers of protection. I'm going to give some examples where this is the easy part, is to figure out what the multiple layers of protection are going to need to be. Then you're married with that for the rest of the life of that facility. You've got inspection, testing, calibration, and maintenance. I'm going to talk about examples of where things can go wrong and have gone wrong. So when I talk about management systems, what is a management system? A management system is very simple. It's a grouping of related business processes, activities, procedures, work instructions, etc. And they describe specific tasks and deliverables that are expected to come from those tasks. And they can be things that involve engineering, operations, maintenance, etc. A whole range of training, HR folks, etc. Now, are there methods out there that are described in terms of management systems? Yes, there are a lot of them, and some of them you're already familiar with. This one you may not be, but it's very similar to some of the things that are already being done under some of the regulations. There's an ISO standard 31000 on enterprise risk management. And as I've shown here on this slide, and this is an example, folks, by the way, still a lot of good seats up front if you can't read that. So don't hesitate to move. Recognition of risks, ranking of risks, etc. There's 7 different items discussed in the standard. I have trouble remembering more than 4 or 5 things. So I try to simplify things and say, okay, a risk management, this is a business process, and this is one I've used for decades in terms of managing different types of risks. And I'm going to step down again and walk through this because this is again a basic concept, and I'm going to be talking then throughout the day about different steps and where things have failed. Now, you identify hazards. All right, we've already identified. We've got a whole list of them we're going to talk about today. Those of you who are using those particular gases or regulate them know that there's been a risk assessment done. And in many cases, those risk assessments were done after there was a serious incident and a standard was developed or a new regulation was put in place. Unfortunately, that's the way we get a lot of regulations because they're intended to address and correct situations that have led to undesired events. If you're installing a system, the engineers designing it, the operators will go through, assess the risk. They'll come up with a risk score, and then they'll determine, is this risk tolerable? Is it a moderate or is it a low risk? However they do the risk rating. So that's the third step. You analyze the risk, and then you ask the question, is this risk tolerable? And there's There are 4 steps in the process, and there are only 5 decision options in risk management. Again, I can't remember anything more than 5, and that's tough. So what are the 5? They're the 5 T's. If the answer to this question is yes, after we put in all of these controls, whether they be engineering controls or a combination of engineering controls and administrative controls, if we can say we've looked at the hazard, we've analyzed the risk, we've done a consequence analysis, we've done a probability analysis, we've come up with a risk score, we put in controls, we say, okay, it's tolerable. Now, if it's not, then what are our options? We can terminate. We can treat. We can transfer. What are some examples of terminating? Maybe we can go to a different gas. Let's say we were going to, for example, on inerting, we were going to use CO2. And then we got to thinking, well, CO2 is more hazardous than nitrogen in terms of inerting for a couple of reasons I'll explain later. So you could say, okay, I'm not going to use CO2, I'm going to use nitrogen. That will eliminate one of the hazards associated with inerting, which I'll discuss in a little while. If you can't do that, maybe you can transfer the risk. Maybe you can have someone supply this material to you over the fence line in small quantities by pipeline. That's what's done in certain industries. You can treat. How do you treat? You do engineering controls, you do administrative controls, procedural controls. After you go back through and you say, okay, we're going to put a couple more controls in, you re-estimate the risk, you look at it and you come back and ask yourself the question, now it's okay. So now I say, yes, it's tolerable, but I've still got one of the 5 T's. I have to tell all of those people who could potentially be impacted and who have responsibility to operate those controls and maintain those controls to understand why that risk control measure is in place. Because, as I will talk about in a couple of examples, there are numerous cases where someone doesn't fully appreciate, they have not been trained, and they do not understand the reason for that risk control. And this gets into something called process safety competency that I'll talk at length about. Monitoring risk controls, inspecting, testing, maintaining, calibrating, doing auditing, which is one of the functions of CUPAs, to make certain that individuals are doing what they said they were going to do to meet the regulations. And hopefully to go beyond regulations and to adopt industry best practices. Now let's talk about management systems and some specific examples where all of you are already familiar with some management systems. So one example is under OSHA PSM and EPA RMP or CalARP. What do we have? We've got a management system, essentially. We've got elements here. Collecting process safety information, hazard assessment, operating procedures, mechanical integrity. These are the components of a management system. Now, are these adequate? Probably in many cases they are, but I'm also going to talk about industry best practices which say we probably need 5 or 6 more elements, and we need to look at these in a little different way if you really want to manage risks effectively and consistently. Now, under the CalARP system, and I'm just going to breeze through this because I think all of you understand this, there are 3 levels. And in some cases, there are exemptions. And I will tell you this, I was the director of corporate EHS for several large corporations in California. We did not have, in most cases, more than 1 or 2 processes that fell under OSHA PSM or CalARP requirements. but we had process safety programs. And we had them in the US and we had them outside the US. And why did we do that? It's because it makes sense from a risk management perspective. And so those of you who are in the operating area, if you have, if you're using propane for a process use, and you have 9,900 pounds of propane, and you're under the threshold, does that mean you should not have a process safety management system? Absolutely not. It does not mean that. There are many things that were not covered in the regulations, which are very hazardous situations. And in places where I worked, we've had 2 belts and maybe 2 pairs of suspenders on to manage those risks. We had a lot of layers of protection that were not required by regulations. So what are some other reasons to go beyond the regulatory requirements if you're under some of these thresholds? Well, one is the general duty clause. There are a lot of reasons someone can get fined if they have a release related to the general duty clause in terms of things that they should have done that they didn't do. So it just makes good sense from protecting an organization against liability, including legal penalties, to manage risks in a consistent manner and not base it just on a regulatory mandate. And there's some examples. Unacceptable residual risk may remain when you're in full compliance. The regulations are generic, and they can't possibly cover all different scenarios and design aspects. And so that's the job of the engineers at the facility, the operators, the maintenance folks, the regulatory professionals, the safety specialists, environmental specialists, to try to address when you should go beyond the regulatory minimum. And then also, as the then CEO of Manville Corporation, this was over asbestos, said you've got to look out in the future because you're going to be judged on the regulations of the future probably in a facility. And when you design a facility to operate for 10, 20, 40 years, whatever the lifespan is, it's likely the regulations are going to get tougher rather than less restrictive. So it makes sense to design, and safety is the management of risk to a tolerable level. Safety isn't the management to meet regulations. Now, meeting regulations may give you a tolerable level of risk exposure. You don't have to go beyond the regulations, but in some cases it makes sense to do so. Now, this is for those of you who are in the private sector and how you manage risk. And I often talk about the 5 steps going from basically trying to respond to violations and poor performance to a regulatory-driven process, to the third one being phase 3, a risk-based approach. And hopefully, most companies are moving towards level 3. Those that are world-class are then integrating all of the hazard controls and environment, health and safety, process safety with their business processes, and then driving for continual improvement. But at a minimum, I'd like to see people at level 3, this phase 3. Now, when we get into the discussion of root causes are almost exclusively, I would say exclusively in my experience, related to management system deficiencies, where there were either inadequate management system practices originally put in place, or they weren't followed. So here are some common deficiencies, and those of you in the back, I'll read some of these for you. These are typically things that are found in process safety management. Closure of process hazard analysis related recommendations not complete or not fully documented. So you go out and you do an audit and you find out that yes, they did a process hazard analysis and they had 30 different findings. Some of them were determined they were going to be tolerated, but there's still 5 or 10 that haven't been addressed. So it's great that they did the process hazard analysis, but there's a management system deficiency when there wasn't action taken and no plan put in place. And no, there may have been a plan put in place, but it wasn't implemented. The last one, mechanical integrity, inspection, testing, calibration, and maintenance. Probably the most common deficiency. You put all of these great risk controls in place, and they're intended to work on demand. That demand may only come once every 10 years or once every 20 or 30 years. How do you know it's going to work? We can talk about some examples where excess flow valves on propane tanks on demand didn't work. Chlorine transfer systems, automatic shutoff valves didn't work on demand. Refinery fires, fuel isolation valves, manually operatable only. There's a jet fire within 20 feet of the valve. Nobody could get near it. So that's another thing. When you put in these controls, you've got to be able to get to them to activate them. Piper Alpha North Sea oil rig disaster in the 1980s. They couldn't get to the deluge system. They'd put it on manual control. The fire started. They couldn't get to the control panel to activate the deluge system. Lost the whole rig and 180 people or something like that. So there are a lot of deficiencies in process safety management systems and how they're implemented. And again, I'm showing this to show you step 4. Most companies and organizations get the first 3 steps right. Where things fall apart is on step 4. They may get it right the first year, but what about 4 years after all that initial training's been done? The preventive maintenance, the inspections, testing, calibration. Suddenly you need that emergency system. It doesn't function as designed. There's some others here. And again, you'll get all these slides. I'm just going to hit a couple of them. Inadequate controls on contractor and subcontractors in terms of auditing, training, and work practice, communicating company requirements, etc. They may not understand, they being the contractors, what all of these emergency systems or preventive safeguards are intended to do. And it is the responsibility of the owner-operator to make certain that happens. But that, again, is a situation that is often a deficiency and leads to some serious problems. Now, chemical process safety. So that's keeping it in the pipes, keeping it in the tanks, preventing loss of containment. Again, take-home lesson. What's the basic difference between worker safety and process safety? Process safety is all about preventing loss of containment. And a risk-based approach, in my opinion, is the way to go. And that's not only my opinion. The American Institute of Chemical Engineers Center for Chemical Process Safety published a book in 2007 on industry best practices that have been developed over the last 40 or 50 years in the chemical process industry worldwide on how to manage loss, how to prevent and then manage loss of containment events. And there are 10 of us who go around the US and the world teaching to these 20 elements. There are 10 of us who are consultants to the Center for Chemical Process Safety. And there are a number of these elements that are a little different than what's in the OSHA PSM or EPA risk management plans. And I'm going to just quickly highlight what those are. And in the upper left-hand section of that slide, there's a book shown that's published by Wiley. It's called Guidelines for Risk-Based Process Safety. And I consider this the Bible for process safety. I was not on the team that helped write this book. I don't get any royalties or anything from selling this book, but I would advise you, if you only buy one book and want to know about risk management systems for process safety, this is the book to buy. Now, how do some of these elements differ? Those that are shown in italics are those that are not under the OSHA PSM or EPA RMP, like process safety culture, like compliance with standards, and knowing exactly what standards apply, having a system in place to update your database when changes to standards are made so that you know why those standards were changed and if they're relevant to your operation and your risk management profile. Process safety competency, under OSHA PSM and EPA RMP, there's a section called process information. Here we talk about process safety knowledge. And what does it take to convert information to knowledge? It's the next thing there, process safety competency. And one of the root causes for many incidents is that process safety competency among engineers, operators, maintenance mechanics, whoever at the site was inadequate for them to understand the hazards and potential consequences of the actions they were about to take. The system they were about to bypass. The system they were about to put on manual rather than automatic control. And so this is one of the things we try to teach in the courses we offer are, how do you make certain that your entire workforce has the level of process safety competency they need. And it's not only the engineers who design the system, it goes all the way through the organization across functions to understand the systems to make certain that they will work to prevent loss of containment. I'll keep going down. Stakeholder outreach. That's not under OSHA PSM or EPA RMP. Numerous situations I'm going to describe during the day where serious accidents happened, where firefighters were killed, was because those organizations did not reach out and make certain that the firefighters understood how do you respond to a situation where you have a potential levy of a tank, whether it's a railroad tank car, a truck tanker, or a stationary tank. And how many of you think that levies only can occur with a propane tank or ethane or butane? You think that's the only case, right? Okay. Anybody else agree with him? Are levies only related to propane, butane, ethane, ethylene tanks? See some people saying yes, others. The answer is no. That gets a lot of the press, but we'll go through that. There are a lot of other liquefied gas tanks that can levy. Process safety competency. Now let's keep going through the list. Conduct of operations. What is conduct of operations about? It's about operational discipline. Let's talk about it. It's not in the talk today, but it's one of the classic examples. The Tosco refinery fire back in 1998 or 97, I don't remember exactly the year. They had numerous controls, operating procedures, training and performance. And this was on a refinery unit. And they clearly stated in the operating procedures, thou shalt not operate above 800 degrees Fahrenheit. And if you do, here are the consequences. Complacency is one of the biggest issues with operating high hazard facilities. And getting complacent and condoning deviations from standard procedures. They got into the habit, for a number of reasons, related to mechanical integrity problems and poor design of instrumentation systems and poor maintenance of instrumentation systems to deviating from the operating ranges. They operated up to 1400 degrees Fahrenheit, and one of the operators went out to look at the other set of instruments that they said we can only count on those being the accurate readings. And where were they located? They were located right at the base of the unit. So when the pipe failed at 14 or 1500 degrees Fahrenheit, who got killed? The operator who went out in the field to read those instruments, because the instruments were not reliable in the control room. But they were running out of the range, and they'd had numerous deviations, and what else didn't they do? They didn't do incident investigations. They didn't look at what are the reasons we're seeing these excursions outside the normal operating range. And so this all comes back to conduct of operations, which is essentially operating discipline. That we say this is what we're going to do, and we will do it every time. Even when the boss isn't looking, even when we know no one is around, we're going to do it the right way. Because there's a reason it's the right way, is to manage risk. And that's part of the other one, which is process safety culture. And process safety culture was the major reason in Texas City at the BP refinery why that happened. They had a lot of others. There were about, when I went through the list here, there were 15 of these were major problems at the Texas City refinery. And they're all documented in the CSB report and the Baker panel report. But anyway, so that's my speech on the soapbox of why risk-based process safety is real important. Now, let's get into what you probably really came to hear about, is types of gases and properties of selected compressed gases, liquefied gases, and cryogenic liquids. So, how many of you know off the top of your head what the definition of a cryogenic liquid is in California? Anybody? We'll go through that. It's a little different in terms of temperature. In most cases, when I'm asked that question, it is a liquefied gas that is at below 150 degrees centigrade. In California, it's below 90 degrees centigrade. So it's a little different. Now, if I tell you that this is filled, that I've got a tank in West Sacramento filled with, it's an atmospheric pressure tank, and it's got liquefied ammonia in it. Is that a cryogenic liquid? It's real cold. It's not, because it's not minus 90. It's about minus, I don't know, it's minus 27 or 28 degrees Fahrenheit. I don't remember off the top of my head what the conversion, but it's not minus 90. So that's an example where it's not a cryogenic liquid, it's very cold. We're going to talk about the difference between compressed gases and liquefied gases too. Now, this is a big business, these compressed gases and industrial gases. If you just look at the industrial gases, which are mainly oxygen, nitrogen, argon, acetylene, not including the feedstock gases for petrochemicals like ethylene or propylene, not including ammonia, not including chlorine, it's approaching a $100 billion market worldwide. I'm not sure the exact number, but that's the right order of magnitude. And about 15% in the US. So it's a big business. The largest tonnage industrial gases are oxygen and nitrogen. And we're going to talk a little bit about them today. And some of the other big ones are carbon dioxide, acetylene. But then the chlorine and propane are real big too. But they're not included in this industrial gas category. And there are a lot of ways to categorize gases. And these are some that you may have seen. Elemental gases or compound gases. They're either elements, diatomic gas like hydrogen. So how many elements, just a trivia question, how many elements are gases at room temperature? Any idea? Is it 5? 20? Anybody got a... It's 11. We'll go through that. Little trivia. Inert gases. Nitrogen, considered an inert gas, right? Not really. It's not entirely inert. For most situations, we use it as an inerting blanketing, but nitrogen really isn't inert, completely inert. And I'll talk a little bit about that. Corrosive gases, SO2, HCl, anhydrous HCl. Refrigerant gases, can be freons, can be ammonia. If we put in liquefied natural gas facilities in California. There was a proposal to put one in Long Beach. It did, I don't know where that is right now, and I think it was postponed. But eventually, if we get a lot more natural gas production on the West Coast, we're going to see some more LNG facilities for exporting. And for refrigerant gases, what do you use as refrigerant gases, do you think, for liquefied natural gas? Propane and ethylene are two of them. Usually mixed gas refrigerant systems. Toxic or poisonous gases. And some gases fall into various categories. For example, chlorine's a toxic gas, right? Chlorine could also fall in the category of corrosive gas. It mixes with water, forms a HCl solution. Nitrogen is an air gas. It's also categorized as an asphyxiant gas, and it's also categorized as an inert gas. So the point I'm making is this isn't really a great system. So I'm going to talk a little bit about how to categorize gases, but there are a lot of different ways, and certain gases can fall under multiple categories. Here are the 11, for those of you who are wondering and want to know. These are ones, that in terms of the elements, that are elemental gases. Some are diatomic, nitrogen, oxygen, fluorine, hydrogen, chlorine. Some are monoatomic, inert gases like argon. Let's talk a little bit about liquefied gases. And when you look at CalARP and federal and state risk management plans, there's some triggers in terms of list of toxics. Federal list of toxics has 77 compounds, 63 on Table 2. And then there are 275 under CalARP in California. Now, in terms of liquefied gases, what percentage would you guess? I don't remember which slide in the order. It comes up soon. In terms of the reason for filing risk management plans, how many of those risk management plans are filed because of liquefied gases? How many think it's 10%? Anybody? How many think it's 25%? Anybody? How many think it's 50%? Anybody? Okay, a couple hands. 2/3. Anybody? Okay. 75%. Anybody? The right answer is higher. 90% or more. We'll go through that. Some of the elemental gases with relatively large quantity uses are shown here. Chlorine, fluorine, hydrogen, and I've shown either the table 1, 3, or 2 threshold limits under the CalARP just for reference. And as I said, just because you only have 90 pounds of chlorine doesn't mean you should be not concerned. I would be. Certainly with hydrogen, if I had 9,900, I'd be real concerned and have a real good process safety program. Compound gases. Compounds mean it's multiple elements. There are a lot of them. And we're going to talk about some of them today, and I've listed again, and these are gases that you will find typically in the state, in your jurisdictions, whether it be boron trichloride in the electronics area, or monomethylsilane, or if you are in a petrochemical refinery operation, or a sterilization facility, let's say, using ethylene oxide, or in a facility recovering carbon dioxide, or using carbon dioxide as a beverage carbonization source. Here's some more. Phosphine, silane, again, electronics industry. The food area, sulfur dioxide. And again, if I've got 9,000 pounds of sulfur dioxide, do I just forget about process safety and those good management system practices like mechanical integrity and incident reporting? And another pet peeve of mine is incident reporting. You go to a facility and you say, what's your close call near miss reporting system like? Tell me, explain it to me. And I look at the reports, and 99.9% or 100% of the reports are related to worker safety related close call near miss incidents to prevent slips, trips, and falls and ergonomic issues. And are those important? Absolutely, they're important. But what happened to all of the process safety excursions when for some reason we got outside the operating envelope we were supposed to be in and we got high level alarms? We didn't get up to high alarms. Those aren't in there. Common hydrocarbon gases, and we're going to talk today about primarily propane. But when you look at this list here, you can see there are a lot of them that are out there. Some are liquefied gases, some are not. So methane. I talked about methane and liquefied natural gas. I don't know how many, there's some liquefied natural gas facilities, but very few. Methane is an example where typically it is handled as a compressed gas, not as a compressed liquefied gas. Now, I spent 2 weeks last month at a liquefied natural gas facility outside the US, and you talk about hazard profiles and risk management needs. Big time. A lot of hazards when you've got very large tanker ship size storage vessels to fill tankers with LNG. And we may have that on the West Coast in the US. We already have them coming in. We have liquefied natural gas coming into the US, and soon we're going to be exporting liquefied natural gas. So it's a risk we're going to start managing. There are about between 100 and 200 facilities right now around the world doing that already. Okay, now I talked about liquefied gases, so which three liquefied gases account for most of the RMPs? Okay, I heard chlorine, what was? Ammonia. What's the third one? What's flammables when they're for process use? So here's the statistics, and this was from 2000. They probably changed a bit, but this is the last time I looked at it. 50% of the risk management plans across the U.S. were filed because of the use of anhydrous ammonia, and almost all of those, certainly not all, but most of them, 90+% were because of ammonia refrigeration systems. 25% were filed because of chlorine, and about 20% because of flammables, for mainly process uses. So liquefied gases are a big deal in terms of risk management plans. Now, in terms of consumption and physical properties, why are these three gases in particular so important? It's because of their physical properties is one answer. It's because at normal atmospheric temperature, when you look at 70 degrees Fahrenheit, look at those numbers in that, so I had my pointer here, right here. Those are manageable pressures. We're talking about less than 250 pounds pressure. They're typically in vessels rated at 250 to 300 pounds gauge pressure. Now, methane is much different, and that's why it's very difficult, it's very expensive to liquefy methane. It's fairly difficult to liquefy ethane and ethylene. Propane's much easier, butane's even easier. Ammonia and chlorine are also relatively easy. I'm going to go back and revisit this, but in terms of tonnages, I also wanted to point those numbers out. In consumption, propane, 250 million tons a year globally, about 50 million in the US. Ammonia over 100 million, and chlorine around 40 million globally. So there's a lot of material. Yes?
Does this change year by year, or is it?
Oh, yeah. I mean, it goes up and down, but this is ballpark. This is close enough. But it does change. These numbers these are numbers typical for the last 4 or 5 years. Now, definitions. We're going to talk about some key definitions and how to define and how they're defined by regulation. So in California, if you look at Section 5194 of Title 8, compressed gas is a gas or mixture of gases having in a container an absolute pressure exceeding 40 psi at 70 degrees F, or it can be an absolute pressure exceeding 104 psi at 130 degrees F, or it can be a liquid having a vapor pressure exceeding 40 psi at 100 degrees F. So there are different definitions, but that's basically, and you will be told if it's a compressed gas typically by the supplier, but this is the exact definition. Compressed gases are typically shipped in gas cylinders or code-stamped pressure vessels that have maximum allowable working pressures. And some examples of those are the bullet-type tanks. They'll sit on the side with 2 dished ends for chlorine, for propane, for ammonia. And then spheres, which you'll see at refineries typical. And those spheres may have ethane, ethylene in them, propane, butane, propylene, etc. We're going to talk about how some of those have failed. Liquefied gases. Liquefied gases fall into a number of categories, and from a regulatory standpoint, you need to understand and be able to differentiate between cryogenic and non-cryogenic liquefied gases because of some exemptions in terms of thresholds. And so liquefied gases at normal atmospheric pressure. So at room temperature, I've got a pressure vessel that this bottle is rated, and it's still transparent, at 250 pounds gauge pressure. And I've got today, and I'm not going to tell you which one, it's either ammonia or chlorine or propane in here, right? So one of those is in here. Now, liquefied gas at lower temperature, I could have, this is an atmospheric pressure vessel now, and I could have ammonia stored at minus 27 degrees F, which would be at atmospheric pressure, because that is the atmospheric boiling point of ammonia. And then I can have cryogenic fluids. I could have liquid nitrogen or liquid oxygen. But I could also have nitrogen or oxygen in this cylinder as a gas at room temperature. But I can never have oxygen and nitrogen at room temperature in this container like this with a liquid. Is that a true statement? Now all of you are saying, wait a second. People in my jurisdiction have they have liquid oxygen and liquid nitrogen. But what are the conditions for that liquid oxygen or liquid nitrogen? When they have nitrogen and oxygen stored at room temperature in a cylinder, it is a gas under high pressure. It is a cryogenic liquid when it's in liquid form. And there's one physical property that will tell you whether or not that substance or element, if it's an elemental gas, can be a liquid at room temperature. Does anyone know what that particular parameter is? Want to venture a guess? What?
In a container that can contain an extremely high pressure.
But what is the physical constant, or I should say parameter, it's not a constant, a physical parameter. It's critical temperature. We'll talk about critical temperature, critical pressure, and phase diagrams and so forth. Now, some commonly transported cryogenic fluids are argon, ethylene, hydrogen, helium, methane, LNG, not so much in the US, nitrogen and oxygen. Commonly transported liquefied gases that are not cryogenic fluids: ammonia, butadiene, chlorine, ethylene, ethylene oxide, etc. Sulfur dioxide. So, I've already given you the answer to this. What measured parameter? Critical temperature. So, critical temperature is the temperature above which a substance cannot exist as a liquid. No matter how much pressure you place on it, you can't make it a liquid. And the critical pressure is simply the pressure at the critical temperature that's needed to cause the gas to be a liquid. So, what are some critical temperatures? Now, if you look down this list, those of you in the back of the room can't see it. So I will tell you. So the critical temperature, let's pick out some examples here. Nitrogen and oxygen. Nitrogen, minus 146.9 degrees C. Argon, minus 122.4 degrees C. Oxygen, minus 118.6 C. When you have that physical parameter known, if somebody tells you the critical temperature of this gas is minus 100 and something, you know that cannot be a liquefied gas at room temperature. And this is what a number of people in the CCPS have asked me to talk about today, because they said this confuses us. Now, ethylene, 9.5 degrees C. So on a cool day in California, if we've got I don't actually know how many ethylene facilities there are in California. Let's say on the Texas coast there are dozens. So on a winter day, when it's 5 degrees C in the morning, and you go by that big ethylene sphere, what's that ethylene like in there? There's liquid. But in the afternoon, when it's heated up and the temperature of the contents of that sphere are now 20 degrees C, there is no liquid ethylene in that sphere because it is above its critical temperature. And no matter how much pressure you put on it, it can't be a liquid. Now let's keep marching up in temperature and tell you why chlorine, ammonia, propane are so important and what some of their properties are. And we're not quite there yet. Propane. These are boiling points. I switched it on you here. This is the column for critical temperatures. Now, all of a sudden, for carbon dioxide, 31 degrees centigrade. So I've got a carbon dioxide container in one of my facilities I inspect as a CCPS inspector. And this one happens to be an atmospheric, a normal atmospheric temperature type situation where I'm not storing at low temperature, so I've got it in a room that is at 20 degrees centigrade. So, do I have liquid CO2 in that container? It's under pressure. It's under the critical temperature. The answer is yes. You have CO2. You have a liquefied gas. Now, on a hot summer day, I've got that CO2 container in a room that goes up to 105 degrees F, which is over 36 degrees C, which is over that number. Now, what's that CO2 in that container? It's under a lot more pressure, and it's all gas. Okay? Now, the reason that propane, chlorine, ammonia are so easily transported, relatively easily transported compared to some of the other gases, is because when you look at these critical temperatures, propane is 97 degrees C, ammonia is 132.4, chlorine is 143.8. These are their boiling points, which are very low, not as low as some of the others. But if you put under sufficient pressure, they will be liquefied at normal atmospheric conditions. Now, let's go and talk about asphyxiant gases for the next 20 minutes or so. And I'll give you some examples, again, of some physical properties. Yes, sir?
I mean, you're describing kind of casually what would be catastrophic scenarios here, right? Where the gas goes from all liquid to all...
No.
Yeah.
That wouldn't necessarily be a catastrophic condition. So let's talk about what we're going to talk about that. That's a very good question, and I'm glad you asked that because I didn't think about that issue being, that's a very good question. I'll address it in just a minute. So, an asphyxiant gas is any gas that can cause suffocation by displacing some or all of the oxygen normally present. Now, I put a note down there in yellow. CO2 and nitrogen are both typically considered as the most common asphyxiant gases. CO2, however, is not only an asphyxiant gas, and we're going to talk a little more about that in a minute. Now, there were some amendments made concerning HMBPs recently, raising the threshold for gases to 1,000 cubic feet at standard temperatures and pressures, right? And one of the reasons to be able to exclude is if you have an asphyxiant gas. And it is only an asphyxiant. So, CO2 is more than just an asphyxiant, so it does not fall under this. If you look at, and I put at the bottom the guidance document that Cal EPA put out in June of 2012, conditions for increased reporting threshold, they have to meet all of these criteria. A gas at standard temperature and pressure, CO2, is a gas at standard temperature and pressure. It's classified as a hazard solely as a compressed gas. Be a gas for which the only health and physical hazards are simple asphyxiation and the release of pressure, and not be a gas in a cryogenic state. So, when you look at number 4, you know now what the definition is. It can't be in the cryogenic state according to regulations unless it is physically there at less than 90 degrees C, right? So that's easy. Now, which of these gases, here are the gases that they say meet that threshold exemption. Compressed air, argon, helium, krypton, neon, nitrogen, an asphyxiant gas, and xenon. All of these can be, these latter ones can displace air and be asphyxiants. Now, where's CO2 used widely? Most wide, in terms of numbers of facilities, it's probably in carbonation of beverages in fast food restaurants, convenience stores, and restaurants, larger restaurants. And also, of course, CO2 is used in solid form as dry ice. And dry ice can cause high CO2 levels in confined spaces. So it also can be a serious hazard if not managed properly. So properties of carbon dioxide. Again, we talked about critical temperature, 31C. So we know that this can be a liquefied gas at up to 31 degrees C. The vapor pressure at 31 degrees C is 56.9 atmospheres. That's a lot. Over 1,000 psi, roughly. Now, let's talk about the other. There's another number here, density of gas. Specific gravity relative to air, 1.5. I want to give you a very easy way, because I don't try to remember these densities. The way I look at it is this. I look at the molecular weight of the elemental gas or the compound gas. And so carbon dioxide, what do I have up there in terms of molecular weight? 44 Daltons, 44 grams per gram mole, 44 pounds per pound mole. So the molecular weight, the average molecular weight of air is close to 29, right? Because you take the percent of nitrogen, the percent of oxygen, there's a little argon, et cetera, some other trace, but it's roughly 28.9 or somewhere around that. So when you look at the ideal gas law, PV equals nRT, you rearrange it to have pressure over the RT and NV, N over V, and you multiply by molecular weight, and voila, you come out with a derivation. Believe me, this is right. The gas density is proportional to molecular weight. So if you have two gases or two gas mixtures, and you know either if they're a pure mixture, if you know the molecular weight, or if you know the average molecular weight of the mixture, you will know the relative density. So I never bother remembering these. I just look at molecular weight and remember that the average molecular weight of air is close to 29. So if I have CO2 that has a molecular weight of 44, the ratio of density of CO2 to air is 44 divided by 29, which is about 1.5. If I have chlorine at a molecular weight of 71 compared to air, it's going to be about 2.5. It's a very simple way to remember, and just look here. What's the molecular weight of the gas? Is it going to be less dense or more dense than air at the same temperature and pressure conditions? And here's an example where I use that. I put the molecular weight, average molecular weight of air is 28.97. Methane, molecular weights, it's less dense than air. 0.55 is the relative density, specific gravity density compared to air. Here's chlorine, 2.5. Very simple rule of thumb that you can quickly make a determination without having to go to a table. Now, let's talk about this whole issue of phase diagrams, and probably you'll never want to use this again, but here's what the critical point is, the critical temperature and pressure. That is the point at which, if you go above that temperature, you have no liquid phase. It's either going to be a compressed gas or a supercritical fluid, but it's not going to be a liquid. And this one happens to be for carbon dioxide. Now, vapor pressure of a substance. If I know the temperature of the contents of this pressure vessel, I've got this hypothetical pressure vessel with CO2 in it. If I know the temperature, I know the pressure. Conversely, if I know the pressure, I'll know the temperature. If it's at completely mixed equilibrium conditions inside the tank, okay? So here's a pressure vessel temperature, vapor pressure temperature relationship, temperature in degrees Kelvin, degrees centigrade for CO2. Now, at 70 degrees Fahrenheit, I said it was close to 1,000, it's 838 psi. So if I know that the temperature inside that sealed container is 70 degrees F, then I know what the pressure is. And this is important now in your question. So how are major hazard liquefied gases is this. So if I'm going to store CO2 in a cylinder at room temperature, and I know that the room temperature during the course of the year and course of the day where it's going to be stored is going to go perhaps from 5 degrees C up to 100 degrees, let's say 10 or 15 degrees C, which is down around 50 degrees F, up to, let's say, 105 degrees F in a storage area. The pressure is going to vary widely. And so what do? I store that in a pressure vessel that can take the upper temperature maximum. So that's why they're designed, when you see CO2, they're designed that way, and they also have to have special design features. For example, when you have a ball valve in a liquefied gas system, where you have a situation where you can go from a liquefied gas to a vapor, the ball valves are specially designed. They have a design that will allow them to relieve pressure resulting from liquefied gas being trapped in the ball cavity when you close the valve. So typically self-relieving seats or a pressure relief hole drilled in the upstream side of the ball. So there's a special design, because you don't want to trap liquefied gases anywhere where they won't be relieved by a pressure relief or where the vessel isn't designed to take that pressure. So carbon dioxide vessels, let me just skip forward. Propulsion, I think all of you know that. I mean, another hazard related to pressure is if you drop a cylinder and break off the valve at the top, you've got a rocket if it's under high pressure. And it will be propelled at high speeds and can kill someone and do a lot of damage. Now, CO2 is stored at both room temperature and lower temperature. Now, to answer your specific question, which was, well, if we have this liquid phase going to a gas phase and the pressure is going to be increasing, can't that be very hazardous? The answer is yes. But these containers for CO2 that are made for ambient temperature storage are typically rated at 2,000 psig for room temperature storage. And at room temperature, the pressure in that cylinder is typically about 800 to 1,000 psig. But as the temperature rises, it can go up to 2,000. And if it gets up to the maximum allowable working pressure on the vessel, what happens? It goes to a pressure relief system. And it will relieve pressure. In vessels rated now, there is CO2 supplied at the lower pressure, in lower pressure cylinders, but it's not cryogenic. And those are typically supplied at something like minus 10 or so degrees F. And these high-pressure, non-insulated cylinders may go up as high as 2,600 psi. The smaller cylinders will contain anywhere from 30 to 150 pounds of CO2. Now, those that are stored where you have the CO2 stored in the liquid form at minus 10 degrees F, those can be at lower temperatures. Lower pressures, lower pressure rated vessels. Now, how many of you think someone has been killed from releases of CO2 in restaurant type environments? I see a couple of hands. Good, all of you know that. Okay, and CO2 is not just a simple asphyxiant. If you have CO2 releases into the workplace, you could have a release that causes the CO2 to drop the oxygen concentration is, say, 19%, which is not highly hazardous. You're starting to get in the dangerous zone. But those kinds of concentrations that would be present at that situation would be over 5,000 parts per million, to be close to 10. And so CO2 has a particular characteristic because when you inhale and exhale, what happens in your lungs? You have gas exchange. You're getting rid of CO2. CO2 is a product of metabolism. And when you have much higher elevated CO2 levels in the air you're breathing, it stops that exchange of CO2 that you're normally having, and it's called carbon dioxide intoxication. And carbon dioxide intoxication can be fatal. And these are the levels. If you get to 1 to 1.5%, slight effect on chemical metabolism after exposure. If you get up to 5 to 10%, breathing becomes more laborious. Above 10%, you could die. And at 10%, the oxygen level is still fairly high. So you can get in like above 19% around. So you would not have an asphyxiation hazard in terms of dying from lack of oxygen, but you could still die from CO2 intoxication. So that's why in terms of inerting, CO2 is a lot more dangerous than nitrogen from that perspective. And I've put in here that I think this needs to be considered on warning signs, which it typically isn't. It just talks about the asphyxiation hazard. It needs to talk about the CO2 intoxication hazard. One of the reasons CO2 is particularly dangerous in areas where it can accumulate is that it is more dense than air. And so it can accumulate near the ground level in the breathing zone. And there are a couple of examples in a fast food restaurant. There was an elderly woman who died in Florida a couple of years ago of a release. And with these lower temperature bulk CO2 systems now, there's a lot more chance in restaurants that you're going to have a release. And so you need some process safety controls in these restaurant situations. Here was another one in Phoenix, and I'm not going to go over the details, and there was another issue in a couple of restaurants. One was in Cincinnati, another one in Florida, where employees were, in the case in Florida, both the delivery person and the employee at the restaurant died. And at the facility in Cincinnati, the delivery person died from release of CO2 and being overcome and dying. And whether it was from asphyxiation or from carbon dioxide intoxication, I don't know. But the bottom line is they died. And there's some other source of information on carbon dioxide asphyxiation and on proper use of carbon dioxide. There's a Compressed Gas Association brochure. Yes, ma'am.
I'm struggling a little bit, and I hope you could clarify the definition of the cryogenic fluid. In the definition that you quoted for California, is stored with storage temperature as opposed to a physical property of the material?
That is a physical property. That is its temperature. It has to be at less than 90 degrees C for it to be a cryogenic fluid.
Do you mean less than minus 90?
Yes.
Oh, okay. Because that's where I was having confusion as well.
Is it the boiling point less than a certain temperature?
No.
Or is it the storage temperature?
The storage temperature. It's the physical temperature of the liquid. It's what it's stored at.
So it's not a physical property of the material?
No, it's the actual state of the physical state of the material in the container that's to be regulated.
So does the definition in California differ from our other national standards like the fire code and the NFPA standards?
The number I have typically used is minus 150 degrees C for cryogenic fluids. I don't off the top of my head know what the NFPA standard says, but as I recall, it was minus 150 C.
Boiling point.
No,
It's not a boiling point
no.
in the definition?
It's the storage temperature.
Okay. So when it's exempted now out of the HMBP requirements,
Cryogenic fluids are not exempted.
well, that's what I'm getting at. In California, it's considered a cryogenic fluid,
Yeah.
but in accordance with the other national standards, it's still a compressed gas. Am I?
Well, no, it may be a liquefied gas. Let me talk to you offline about that, okay? Now, what I'm going to try to do very quickly is show you, let's talk about nitrogen, the other one, and I'm going to show you a video first. Why do we use inert gases for blanketing? Typically to prevent degradation of a product or to prevent getting into the explosive range. We'll talk a lot about that when we get into flammable gases at the next session. No good deed goes unpunished. Unfortunately, one of the hazards associated with inerting is asphyxiation. And we still have far too many asphyxiation deaths. And this is one that, these are some that happen.
Workers who have survived these episodes
Yes, thank you.
describe a funny feeling where they can take a deep breath and yet they still feel like they're suffocating.
On November 5th, 2005, 2 workers died at the Valero Energy Corporation refinery in Delaware City, Delaware. They had entered a reactor vessel, a confined space that was filled with nitrogen, an odorless, invisible gas. The accident occurred during a maintenance operation at the 5,000-acre facility, which processes 180,000 barrels of crude oil per day. The complex is one of Valero's 18 U.S. refineries and has 570 employees. The U.S. Chemical Safety Board investigated the accident and issued a case study with safety recommendations.
This is not a new issue for the CSB. In fact, the board conducted an earlier investigation into the hazards of nitrogen asphyxiation and issued a safety bulletin in 2003. The bulletin identified 85 nitrogen asphyxiation incidents that occurred between 1992 and 2002, killing 80 people and injuring 50. That study and incidents since it was issued in 2003 show that lives continue to be lost because workers are not being made aware of the dangers of oxygen deprivation.
Oxygen comprises 21% of the air we breathe, and humans cannot survive for long when it drops below about 19%. In refineries and chemical plants, dangerous, low-oxygen environments are created when inert gases like nitrogen are used to remove oxygen from pipes and equipment.
The risk of an oxygen-deprived atmosphere is that you'll get trapped in that situation. You'll get trapped and die.
Dr. T. Gadati is a physician and chairs the Department of Environmental and Occupational Health at the George Washington University. He describes the effects of oxygen deprivation on workers.
From the moment a person first goes in to an oxygen-deprived atmosphere, they are effectively impaired. And when the oxygen-deprived atmosphere begins to enter the lungs, the oxygen in the blood that's going to the brain starts to fall. That affects the brain's judgment, it affects coordination, it affects the ability to exert strength. They fall down, fall unconscious, or their judgment is so impaired that they can't find their way back out, and they die.
The CSB case study on the Valero accident underscores the importance of strict safeguards when working around low oxygen environments. Workers are in danger not only inside confined spaces, but also around openings where inert gases, like nitrogen, are flowing out. Here's what we believe happened the night of the accident. Valero's hydrocracker reactor number R1 was shut down for maintenance. A large pipe elbow had been removed, creating an opening surrounded by large steel bolts in the middle of the platform. Workers had wrapped red tape around the bolts and covered the opening with plywood and plastic. Nitrogen flowed into the reactor and exited from the covered opening. Nitrogen is invisible, but it is colored light green here for illustration. Workers had attached a sign reading, "Danger, confined space, do not enter without permit." However, there were no specific warnings posted about the nitrogen hazard. A crew of Matrix contract workers had received a Valero-issued permit to reinstall the pipe elbow. The safe work permit did not warn the crew that the reactor was filled with nitrogen. In fact, the permit stated, quote, nitrogen purge NA, not applicable. 2 contract workers removed the plywood cover and cleaned the ledge around the opening. At about that time, a 3rd worker noticed a roll of duct tape lying 5 feet down inside the reactor. This presented the crew with a problem. The tape would cause the reactor to fail Valero's cleanliness inspection, and they would not be allowed to reinstall the elbow until it was removed. However, entering the reactor to remove the tape would require obtaining a specially trained and equipped crew and a confined space entry permit from Valero. That process would take many hours and delay the installation of the elbow, which was to be completed before the end of the night shift, now half over. In addition, the crane needed for lifting the 5-ton elbow into place had just become available for a short period. To avoid the long delay, one worker stood near the opening with a long, flexible wire and made several attempts to hook the tape. But he was unsuccessful. What seemed like an easy task just wasn't working. Most likely, the worker then got closer by sitting on the ledge of the opening with his legs dangling inside. But he still could not remove the tape. Based on the evidence, the CSB developed 2 possible scenarios for what happened next. In the first scenario, the worker lowered himself into the reactor to quickly grab the tape, relying on his foreman nearby to insert a ladder so he could climb back out. But after lowering himself into the reactor, he inhaled the nearly pure nitrogen inside. Deprived of oxygen, he quickly collapsed. In the second scenario, the worker on the ledge leaned over the opening, trying to get closer to the tape. At that point, he either accidentally slipped into the reactor, or he breathed in the oxygen-deficient atmosphere just above the opening, lost consciousness, and slid in. What happened next added to the tragedy. An eyewitness saw the foreman and the contract administrator peering into the reactor. The stricken worker was lying unconscious inside. The foreman quickly inserted the ladder into the reactor and climbed down to help his fellow worker. But without a breathing apparatus, he too collapsed from the lack of oxygen. The contract administrator declared an emergency on his radio. Valero operators then sounded the unit alarm. When company emergency responders arrived a short time later, they saw both victims lying motionless inside the reactor. A handheld meter inserted through the opening showed less than 1% oxygen, a lethal atmosphere.
I'm going to cut the video short just because we're running out of time and just make a couple of comments. These are tragedies, and I was just at a facility teaching that process safety course that had been built during 2005, 2006, and when we talked about this subject, they said, oh yes, we had 4 people die during the welding of a 48-inch line. One of the welders went in, argon atmosphere, didn't come back out. Another one went in after him. He didn't come out. Somebody else went in. 4 people died. So this is all to happen now. Many of you will not necessarily run into a situation like is shown here, or a welding with large pipes. But there are other situations with asphyxiation hazards that you have to be aware of. For example, if you have a facility where you have dewars of nitrogen, liquid nitrogen stored, that vent. They're typical. So you have the liquid nitrogen at cryogenic conditions in a container that's rated at 250 psi. As that, and it's well insulated in the dewar in the vacuum jacketed vessel. But as it vents, or as it heats up, over the period of time, every now and then it will vent. Sometimes those vent valves can stick open, they can freeze. And what happens then, you get a large discharge of nitrogen vapor. I have gone to facilities where I've worked and found that they have moved the dewars into small utility closets and storage rooms, and then and the doors closed. And so if you walk in there after it has been vented, after it's been venting, you can get into an oxygen deficient atmosphere. So what I did was I insisted, take the door off. Either put an oxygen sensor in there with an alarm or take the door off, preferably the oxygen sensor, and warn people of that hazard. Now, when you get the slides, you'll see information on nitrogen, and I talked about this issue of whether nitrogen is a liquefied gas or a compressed gas. So with nitrogen, because of its low critical temperature, at room temperature, nitrogen will look like this inside the vessel, not like this. If you are in a room with a cryogenic fluid in the container, inside that cryogenic container, the nitrogen will look like this because it will be at a very low temperature. But if it's in a compressed gas cylinder, at room temperature, it will be a gas. Now, I'm just going to show one more slide here. Whoops, here. This one. During that period, 10-year period, 8 deaths per year resulted from nitrogen asphyxiation. When we talk about lessons learned, we keep having to relearn the lesson about asphyxiation hazards. So hopefully in your jurisdictions you can help make certain that even if it's outside your scope, if you see these situations, especially with situations with dewars of nitrogen, that could be in a small room, that could be a real issue. So I look forward to seeing many of you back for a discussion of flammable gases starting in about 10 minutes.